Hello and welcome back. Now in this video I want to look at a problem that I've had for quite some time, and you might also have had this problem or still have it. It is related to laboratory power supplies and the ripple they generate. Now the supply works quite well. I mean, you don't notice any problem by using it on its own, but if I connect it to an oscilloscope, then something interesting happens. So this is the noise that my oscilloscope generates on its own. So right now my probe is connected to the ground lead and I'm reading about 8 millivolts of ripple. So this is quite okay for this type of cheap oscilloscope. Now watch what happens when I connect this thing to my power supply. So I'm only connecting this to the ground input, so not the signal input, and I'm getting more than 100 volts of ripple, which is, quite frankly, unacceptable, especially if you're trying to make low noise measurements. I mean, you can't even analyze a power supply or anything, one that you're working on, because of all the noise that the initial power supply is generating. And the odd thing about this noise is that it's not necessarily the output noise of the laboratory supply, because to measure that you would need to be probing both of its inputs. It's noise coming through the ground system somehow. And I sometimes get this problem, sometimes I don't. Now, in the past, I've used this massive filter to filter out the noise, but in the meantime, a box fell over it and it kind of broke into pieces, so I'm not going to be using this thing anymore. And this is not the right way to fix the problem. The sad thing is, you only need one component. With a single component, you can get rid of most of this ripple. You just need to know where to put it. So if you're curious where this ripple is coming from, how you can simulate it using LTspice, and of course how you can fix it, then keep watching. So let's start things off by talking about the power grid and how you get electricity from the grid into your device. Basically, the typical electrical connector has 3 wires: the live, the neutral, and the protected earth, which can also be found under different names like earth ground or something else. Now, when you're getting energy from your grid into your unit, you're using either all 3 of these wires or just 2. So what I got here is an example connector from my country, in which I only have 2 wires, the live and the neutral, and then we have this sort of connector, in which you have the live, the neutral, and also this protected ground. So the 3 wires go into your unit, and the actual power comes through the 2 wires, so the live and the neutral. Then inside you probably have an isolation transformer, and from this you're powering your device. You rectify it and so on. And this is where you get your local ground inside your unit. Now the protected earth is there mostly as a safety measure. So this might be connected to the housing if the housing is made from metal, like is the case in washing machines or the power supply. Let's just check this with the multimeter set to the continuity function. So we take the plug that the power supply is connected to, and if we check the protected earth, it's not connected to the ground, so the output ground of the supply, but it is connected to the casing. So through this screw we have a direct connection to the protected earth. But usually it's not connected to the local circuit ground. But there are some exceptions from this rule, of course. Now if you have 2 units powered from the same grid, and these 2 units interact, like let's say your computer is sending audio information to your amplifier, then usually the ground is interconnected between these 2. And that's not a problem, since this local ground is completely isolated from the electrical grid. Now, as I said, in certain cases this protected earth is not really completely isolated. One device that is built in this manner is the oscilloscope. So normally every oscilloscope will have its local signal ground referenced to the earth ground. So if we check the continuity with the protected earth on the oscilloscope, well, it's not connected to the casing since that's plastic, but it is connected to the ground of the probes. So all of the outputs of the oscilloscope have the ground directly connected to the protected earth in the power plug. Since all the measurements you want to make should have a very stable reference, which is the earth ground. Now, when you connect your oscilloscope to any other circuit, like the power supply, you're connecting this completely floating ground to the earth ground. Now, this normally should not be a bad thing. I mean, this protected earth is there to protect you, so it's supposed to do good things. But is it? Now, to get a better understanding of the requirements and the specifics of designing circuitry intended for being supplied from the electrical grid, I highly recommend this document from Power Integrations. Basically, they go over some power supply design techniques. So this document is specifically written about power supplies and how you should design them for electrical noise emissions and safety. So it covers the various emission standards that such devices need to comply with, how you're measuring these, what are the various safety principles and requirements behind this type of equipment, the various ways in which you can connect to the AC main supply, so 2 wires or 3 wires, and then how you're going to build your EMI filter. And then they go over the various typical noise sources in flyback supplies, so both differential noise and common mode noise. Now in our case, we don't really want to design an input filter or anything, we just wish to first of all understand how such a supply is built. Now this document is great not just because it covers switching supplies, but because it covers flyback type of switching supplies, the exact type of supply that my laboratory power supply is. So here they're giving an example in which 2 wires are used to supply the circuitry, but we're more interested in something like this. So this is not the supply that I have, but it's very similar. So basically we're supplying the unit through the live and the neutral wires. We've got our input filter, rectifying bridge, the transformer, and then on the secondary side a rectification diode, and then an output capacitor, and then the circuit can supply something else. Now, I previously mentioned common mode noise and differential noise. Now, in short, differential noise usually goes between the 2 input or the 2 output wires. So for example, we have differential noise between the live and the neutral wires. So it's noise that goes through the live wire and then back through the neutral. Or if we look at the output of the supply, it goes out the plus wire and comes back in through the ground wire. And common mode noise is something a bit more difficult to explain. Basically, it's a kind of noise that comes in through both supply wires and goes out through both supply wires, and then closes around in a more complicated manner. Now, inside the flyback supply, we have an interesting source of common mode noise because of the connection between the primary and the secondary. So the 2 sides are galvanically isolated, there's no direct connection between them, and this is done for safety reasons. But the noise in the primary side couples to the secondary through stray capacitance inside the transformer, and then this noise is supposed to close back, so the noise should be kept inside the power supply, shouldn't go outside, through capacitors connected from the ground back into the ground of the primary side. So in this case C8 and C7. Now in between these 2 capacitors is also the protected earth, and we'll get back to this. So before starting to simulate the circuit, let's do one more thing, and that is try to measure the noise that our supply is generating. So we can start by looking at the common mode noise. So common mode noise can be defined as the noise that comes out of the supply and closes back through the earth ground. So we can measure the noise, and we know that the oscilloscope is connected to the earth ground directly, so I can simply connect to the output of the supply. And we can see that there's quite a bit of noise here. So first of all, we can see this 50 Hz oscillation, so basically this is the mains voltage, but we only see a 5 volt peak to peak remaining from it. And if we zoom into this thing, we can see something that's quite characteristic to flyback supplies. So this thing is quite high voltage peak to peak. We can see the switching and then this oscillation going on. So this will be a thing that will be interesting to try to simulate. Now, another thing that's interesting to notice is that we're getting the exact same thing if we measure the plus output. So this common mode noise is coming out of both of the outputs of the supply, and we're getting the exact same thing from either. Now, just like before, if we connect the ground of the probe to the ground of the supply, and we short circuit the probe, we're gonna get this thing. So this is an oscillation going at around 400 kHz, and it's modulated at around 70 kHz. So most probably 70 kHz is the switching frequency of the power supply, and then this 400 kHz is some sort of ringing or oscillation going on through the system. Now, an interesting thing to notice about this, so right now we're getting around 90-100 millivolts of peak-to-peak noise. Now, let me show you something. Basically, I've unplugged the supply, and if I take a bit of electrical tape and isolate the earth connection, so don't try this at home, this is just for experimentation purposes, so this is highly not recommended. So right now I isolated the earth connections, but the supply can still be supplied. And now if I plug it back in, so the supply starts working again, but the noise has disappeared, so the connection is still there. What this is telling us is that the noise, the 400 kHz noise, has something to do with the earth ground. Because by removing the earth ground, we're left with only around 15-16 millivolts of noise, so quite decent. And if I try to measure now the differential noise, so the noise coming between the outputs of the supply, we get the same 26 something millivolts. So the supply is not that bad. I mean, its differential noise is quite small, it's just that the common mode noise is large. And now we can start simulating using LTspice and try to find a way to reduce the noise that the supply is generating without isolating the earth ground, since this is not a solution. Let's see what we can do about this. Now, I won't be simulating the entire circuit because it would take forever to simulate, and because I don't have the actual schematic of the supply. I mean, I know it's a flyback type of supply, but I don't have the exact schematic. So, to begin with, what I got here is a simulation involving the electrical grid. So I got my power supply, then the laboratory supply itself is represented by having the input filter, some rectification diodes, capacitor and a load, and then the secondary side again has a voltage source, output capacitor, and then the capacitors linking both the primary and the secondary side to the protected earth. On the oscilloscope side, I have my protected earth connection, and then a basic representation of the resistances found in the oscilloscope. So my input divided by 10 resistor network, and then a 1 ohm resistor to represent the wiring going through the ground system. So let's start off by simulating connecting the oscilloscope to the negative output of the supply. And if we do this, we get nanovolts of voltage, so we can't really read anything. It's nowhere near the actual measurement that we've done. So something must be missing. And the missing element is the stray capacitance inside of the transformer. So because of the way the transformer is being built, there is a bit of capacitance between the primary side and the secondary side. Now if we include this, so basically putting in a 100 picofarad capacitor, the actual value might be higher or lower depending on how the transformer is built. Now if we resimulate this, we see something completely different. This time we have the exact same shape that we have in real life. So right now the simulation looks exactly like the measurement. Basically this is the 50 Hz voltage from the main supply pass through the diode network. Now the voltage is slightly smaller than the one in real life, but this has to do with the capacitors and components that I didn't really place inside the supply. But the shape is correct. Now the next thing we can look at is what happens when we disconnect the protected earth. So we've seen that this helps, but it's not something recommended. And if we simulate, we can see one of the reasons why. Using the same setup, I'm no longer getting a 1 volt or 2 volts or 5 volts of ripple, I'm getting a 300 volts of ripple. Basically, the mains power supply is directly coupled through this stray capacitance into the oscilloscope. And in the simulation I'm getting roughly 310 volts, and in reality it's around 360 volts. So my mains voltage might be a bit larger than this 310. You can never trust the electrical company. So now moving on, reconnecting things. Let's see what happens if we actually add the ground connection of the oscilloscope. If we look at the output, I mean, we're seeing a bit of ripple, but it's extremely small, so it's in the millivolt range. It has nothing to do with the actual measurement. So the thing that we're missing at the moment is the actual flyback supply. So until now, I just simulated the power supply as a load on the input side and as a generator on the output side. I didn't really simulate the flyback supply itself. And for that, I will make a completely different simulation because of the way it slows down the simulation if I simulate everything starting from the electrical grid. So the important thing that we've learned from this part is that we have this stray capacitance, and this is something that we need to include in our next simulation. So what I got here is basically the same thing, only this time I'm supplying directly from a 300 volt DC supply. I got a generic flyback circuit with stray capacitance added between the primary and the secondary side. I also have the capacitors going from the supply lines both on the input and on the output to the protected earth. And this time if we simulate and look at what we're getting on the output, we're getting a waveform that is very similar to the one that we actually measured when we zoomed into our first measurements. So basically this is what I measured when I connected only the tip of the oscilloscope without the ground lead. Now, to make the two a bit more similar, let me just invert this. And now the two waveforms are almost identical. So if we compare this to when the switch is switching, we can see that during the moment that the switch is turned on, we have this spike, then the coil discharges, and then it oscillates until the next switching cycle. So exactly what we're seeing in real life. Now with this circuit, if I now connect the ground lead of the oscilloscope to the output and look at the output voltage, I'm starting to get a bit of noise, much higher ripple, but it still doesn't look like the actual measurement. Now there's one thing missing here, and that is that in the simulation the protected earth is connected to the oscilloscope through an ideal piece of wire. Now in reality it's not an ideal wire, it's about 2 or 3 meters of electrical cable that has some resistance which let's say we can neglect, but it does have some inductance which we cannot neglect. So if I simply add, let's say about 5 or 6 microhenry of inductance, the waveform changes completely. And this time the waveform does look like the measured thing. So basically what we're seeing here is energy coming from the switching supply, coupled through the transformer, through the stray capacitance, and then causing a ringing through the protected earth supply network because of its inductance. So the voltages are not exactly the same, but the phenomenon is being reproduced correctly. Now another interesting thing you might notice right now is that I'm measuring 100 something millivolts, and this voltage is coming across this internal 1 ohm resistance of the oscilloscope, and that means that there's 100 something milliamps of current going through there. So what we're seeing in the oscilloscope when we connect the ground is that current is coming from the supply discharging into the protected earth, and this is not something that should happen. So this noise, this energy, is coming from the switching node, so from the switching action of the supply, and this is coupling through the stray capacitance, and normally what would happen is that this energy would close back through the capacitors inside the supply. So we have quite high spikes of current going through this output capacitor. But not all of the current goes through there. Some of it is coming through the protected earth and causing us problems. So this is basically giving us an indication of what's going on and how we can fix it. So our problem, the root of the problem, is that the supply is noisy and that the initial capacitors which were placed in there to keep the noise inside the supply are not doing a very good job. Basically, when I connect my oscilloscope through the protected earth, the impedance of the connection has a close value to the impedance of the output capacitor. So the capacitor from the output to the protected earth inside the supply. Now, there's two ways to keep the noise inside the supply regardless. Either increase the impedance of this external connection. This is where disconnecting the protected earth helps, since this way the noise can no longer be coupled through the external circuit, but we're not allowed to disconnect the protected earth since that's not safe. We can add a very big inductance on the line. So let's say if I add 10 millihenry, then the noise coupling through it will be neglectable, so microamps. But again, this is not something that you can really do, especially since the supply is a 5 amp supply. So you need to make a 10 millihenry inductor that can handle 5 amps. Now of course 10 millihenry is not really necessary, but you would need a high inductance to actually filter this out. But a better thing that can be done, without actually overcomplicating the supply, is work on this output capacitor. So the capacitor that's connecting the output to the protected earth. Now at the moment it's at around 20 nanofarads. But let's say we increase this to 400 nanofarads. By doing this, we didn't get rid of the noise, but we did reduce it substantially. So we went from hundreds of milliamps to tens of milliamps. So at least a tenfold reduction in noise can be obtained just by increasing this capacitor. The only thing to look out for when doing this is that this capacitor needs to be rated for high voltages, so at least 400 volts. That's why you can't really put any sort of value here. So if you would put 10 microfarads, it would be better. But 10 microfarads at 400 volts is a huge capacitor. Now there's one thing to mention here. So in case you're planning to modify your supply to add this thing, the manufacturer of the supply, whoever it is not really responsible if you break your supply. So please proceed with caution. Any sort of modification to the supply could end up destroying it. So modifying any sort of equipment you need to do at your own risk. Now let's have a look at what's inside this thing. So basically this is the circuit. It's not very complicated. So on the left side you've got your input mains power circuitry, input filter, input capacitors, rectifying bridge, and so on. So don't mess with this area since this works with high voltages, and of course only open the device if it's unplugged, so be safe about things. Then you got your transformer and then your secondary side. So here's the rectifying diode for the secondary, first filtering capacitor, a permanent load, an inductor filter, another electrolytic capacitor, and here on top, I'm not sure how well it's visible, we've got our first capacitor, which is connecting the ground to the earth. So this screw is connected to the casing, which is connected to the protected earth. And then we got a bit of wiring going to the output. So here are the two connector plugs that go outside. And here again, we have some capacitors which link the two wires to the protected earth. So now the question comes with my massive capacitor. Where do I put it? Do I put it right here on the board? Do I put it down here at the connector plugs? Is there a difference between the two positions? So I think we need to simulate things in a bit more detail to find out where exactly to put this thing. And we can simulate this by splitting up our initial 20 nanofarad capacitor into two 10 nanofarad capacitors and adding, let's say, 100 nanohenry of inductance for the wiring in between. So if we add it at the beginning, we have around 15 milliamps of peak current and a bit of noise. If we add it at the end, we get slightly more current. So what we're seeing from this is that the closer the short-circuiting capacitor is to the noise source, the better it will act. So one way of doing this is either closest to the noise source or splitting up the capacitor into two separate capacitors with half the value. So I added the capacitor from the ground to the protected earth. So this is the 470 nanofarad capacitor, but I also added an extra resistor. So this is a 4 mega ohm resistor, and the whole point is that you don't want this capacitor to charge up with certain voltage that could discharge and create some damage. So it's common practice to also add such a resistor to unload the capacitor, but a high value resistor, so not 100 ohms or something. Now of course this capacitor is not sitting very well here, so some sort of proper fixation will be in need. But for now, let's just see if this actually helps, if the theory and the simulation actually looks like what we have in real life. So I'll just have to put things back together now. So now let's see if that modification worked. I removed the tape from the earth connection, so the power supply is properly earthed this time. Now if I take my oscilloscope probe, connect it directly to the ground, and run, the noise almost completely disappeared. So we're still getting some common mode noise, but this time it's much smaller than before. So we went from the nearly 100 millivolts down to 20-30 something. So now the supply is far more usable. Now if I disconnect the oscilloscope, so just to see where my noise floor is, we can still see that connecting to the power supply still adds a bit of problems, so the solution isn't perfect, but we're getting there. I mean, it's much better than it used to be before. Now another thing we can try at this point is work on this inductance. So if we would have a larger inductance, and we would resimulate this, we would notice that current is going down. So we're building a better and better filter, the higher this inductance is. And at the moment, this inductor is only formed from the wiring existing between the power supply board and the output connector. Now you could add inductors in here, but they would need to be rated at 5 amps at least. And that's not a very cheap inductor. The second thing you can try is add this sort of thing. So this is a ferrite clamp. This can be found in all sorts of equipment, simply clamped over supply wires. And the way this acts is by increasing the inductance of the wire by adding this ferrite over it. Now if you don't have this sort of thing, you can simply use a ferrite ring. So this again can be found in all sorts of circuits. Usually there's a bit of wire around it, but you can simply take the wiring from your supply and just thread it through this thing. The more times you thread it, the more inductance you're getting. And this way you can increase the inductance of the wires and create a better filter. So that's the theory. Let's see how this thing actually works in real life. So what I did was extend the supply lines, so from the board to the connectors, and add this ferrite ring. So basically I wound the supply lines around this ferrite ring a few times to create a basic common mode choke. So I added inductance on both wires, so both the plus and the minus, and by putting them on the same piece of ferrite created the common mode choke. So now let's see if this actually helps. So now with the final inductor added, let's just see the noise that the supply generates. So we're still getting a bit of noise, but it's a bit lower, so we went from around 30 millivolts down to around 20 millivolts. So this common mode choke did actually help, and we're getting the same thing on both outputs. So in the end I managed to reduce the noise of the power supply quite substantially just by having some very simple measures. And this is all thanks to properly modeling and understanding where the noise is coming from. So just to recap, we went from this sort of noise, so this is on a 20 millivolt per division scale. By adding the capacitor we went down substantially, so most of this noise simply disappeared just by the addition of the extra capacitor. And then when we added also the common mode choke, we went down even more. So you might not see a very big difference between with or without the common mode choke, But you can see that a lot of these little spikes, so most of this high frequency noise has been reduced. So all in all, if you have a noisy supply, you can try out these measures. But of course, be careful with what you're doing, so don't get electrocuted since the power supply usually works at high voltages, and try not to break the supply, because any sort of modifications you will do inside of it is at your own risk. With that being said, hope you got some useful information out of this. Leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.